Hi, so today we're going to be looking at the product or productorial operator or symbol. So, well, you might have heard of the summatory, which is a symbol or operator which sums the terms inside it. For example, if we call S this, sigma stands for the summatory of something, and we go from k equals 0 to n of some thing inside, some function of k, then this just represents the sum of all these terms, a0 plus a1 plus dot dot plus an. But what is n? Well, n has to be some kind of integer, positive, non-negative integer. So this will actually be equal to 0, 1, 2, and so on. Okay? Now, it's a natural question to ask, what if instead of adding, we multiply them? And this is precisely what we're going to be doing. Instead of an S for sum, we're going to write a P. And let's say that we choose capital Pi. Right? Instead of sigma, we're going to choose capital Pi for our symbol. And let's just call this n, and again, we are going to get exactly the same, but instead, we have this. Instead of adding, we are multiplying. So up to some an, where again, n is just this, right? It's some number, some non-negative integer. This looks like a 9, but of course, this should be an a, okay? So let me just erase this and put it here. Say some properties that are quickly deduced from this. I will make more videos going more in depth, but this is some kind of a quick introduction or a notion of what a productorial is. So, well, let me just erase all of this and put it up there. So P is just the product from k equals 0 to capital N of some term ak. And this is just a0 times a1 times dot 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 times an. So let me just erase all these real quick. Well, it's getting too dirty, but so there are some properties that are really quickly deduced from the definition or from this expression. So what happens if we have some ai equals to 0, where I, well, is less, let me just say that I is greater or equal than 0 and is equal than n. Well, this implies that p equals 0. And let me just say this a little bit more in depth. AI is some term between. So let's say that we start at a0, a1, and we keep on going till we get to ai, and after ai, we keep on going till we get to an, right? Because I is greater or equal than 0. It can be 0, but it can be any other number, but it's less or equal than n, so we don't go over. So if this happens, then the product is 0. Why? Because the multiplication of any finite numbers times 0 will always be 0. So that's the first thing. Now, what if AI is greater than 0? Well, if we again do this for all of the i's, well, this of course implies that P is greater than 0. Why? Well, because if all the terms that are multiplying are positive, there's no way that you can have a negative product, right? Because positive times positive and so on gives positive. Nevertheless, for the negative counterpart, right? If AI is less or equal than 0, will we have some kind of problems, right? So, sorry. Not really problems, but we have to think of a way to summarize the result. So that is, if it's negative, what will it be? Will the product be positive? Will it be negative? Well, it depends. So let me just say that there are an even number of terms that are negative. So let's say there are an even number of negative terms. AI is equal to 0. So if this happens, if they're even, then the product will be positive. Why? Because we will have that maybe A1 is negative, maybe all of the rest are positive, but some other guy is negative. 2 is an even number, so they will be positive, right? Likewise, if just the same but with an odd number of AIs, right? This just means that it's exactly the same sentence, but with an odd number of AIs, we will get that P is less than 0, because we have negative times negative is positive, but that's even, so we need another one to make it odd, which will mean that it's negative. A nice way to put it is that, let me just try to put it in a more formal way. So, this implies, well, depending on, let's just define a function count. Count AI over 2 belongs to the natural numbers. This implies that P equals 0, greater than 0. And if count AI over 2 is not a natural number, then P is less or equal than 0. And this is some kind of computing notation, right? The count function. But well, I think it's a nice way to understand it. So what I mean by count function is that we are going to be counting the number of terms that there are. For example, if there are 6 terms which are negative, count AI will give us 6. 6 over 2 is 3, which is an integer, which means that we will have positive. If instead count is an odd number, this will mean that it will not be divided by 2. So the result of this will not be an integer. This is not really a too mathematical notation, right? It's just a computing notation, but I think that's some nice way to put it. But well, let's just get rid of this and get into more interesting stuff. So this was just a really quick comments I want to say. Well, now another cool property is that, for example, when you have a sum of AK plus BK from K equals 0 to N, you can actually split this up. Of course, if N is not infinite, and if N is infinite, it will require that both sums converge, but not getting to that now. We usually will be able to split this into 2 sums. That is, we will be able to write this plus this with the same limits. Nevertheless, as you might have guessed, this does not work for pi. If we try to do it, this will actually make no sense, because we are adding a plus bk, but this is equal to a naught plus b naught times a1 plus b1, and so on up to an plus bn. And this is not equal to the product of A times the product of B. Okay, this is not equal to this. Let me just write this. This is not equal to the product of AK plus the product of BK. Which, well, this would be just A naught, A1, so on up to AN plus B naught, B1, Bn. Of course, this does not hold. Maybe in some special cases we can find some AK and BK which, for which it is satisfied, but in general, this relation does not hold. Nevertheless, there's a much cooler relation that doesn't hold for the sigma, and that is, instead of writing a plus, let's just write a multiplication, or even a division. But let's start with multiplication. Well, this is just, well, a naught times a1 dot dot an times b naught times b1 dot dot bk. And now this we can split it into 2 products. The product of AK, well, maybe too big of a pie here, of AK times the product of BK. Likewise, if we have a division, and of course if none of the BK are 0, we have the following relation. So if we have that instead of multiplying they are dividing, then we can write, well, as long as BK is not 0 for all K, sorry, this should be okay, Then we can split this up into the top product and the bottom product. Okay, so this will be really useful when we are working with the so-called recurrence relations. And what a recurrent relation is an equation of the form, let me just say an plus 2 equals to n plus 1, n plus 2, I don't know, and n squared times an. So this product is going to be really useful for relations of this kind, in which we want to find the general term an, and from it solve the equation and find all the other terms. How will we proceed? I'm not going to be doing it now, maybe I'll make some more videos about it, but it's divided by this, assuming that an is not 0, then take the product and use these properties in order to separate it into one product, two products, and the bottom product. So it doesn't have to be exactly of this form, but if you have some terms that are multiplying or dividing, it's extremely useful. I have a video about Legendre polynomials and Legendre differential equation, in which, not exactly this relation, but other one, which are a bit, I think it's harder, in which we use the product notation to solve it. And you see that's extremely useful. And to make it even more useful, we are going to be using a really cool identity that I'm going to put right here. So let me just erase this. So this product is really good and it's alright, but we can make it even stronger by defining some special products, right? Or by realizing that some special products can be expressed like this. For example, n factorial. This is just n times n minus 1 times n minus 2, 2 times 1. And this can be expressed really easily in product notation as well, where let's just say that we're going from 1 up to n. And what are we going to be multiplying? Well, we're going to be multiplying k, right? Why? Because, well, if k is 1, we get 1, 2, 2, and so on up to n. But instead of capital N, this time, let's just write little n, a lowercase n, because we have this expression. Now you can change indexes just like you would do with summation. For example, let me just say that I define m being equal to k minus 1. Then the limits will become, well, if k was 1, what is m? M is just 0, and if k was n, n just becomes n minus 1, right? And k, well, if we isolate k, we get that k is n plus 1, so we get n plus 1. And this would also be n factorial. It's a more strange way to put it, but this is exactly the same expression. A really nice trick to make changes of indexes is, for example, say that I subtract 1 here and here, right? 1 minus 1 is 0 and n minus 1 is n minus 1. And we add 1 in the function inside. Sorry, this should be a k. Well, no, it is an m plus 1. But instead of m, we can write just k or whatever. I'll make some videos talking about changes of indexes, because I think it's something really important. And now, well, this is a really easy product, n factorial. But let's say that we want an even factorial, 2n factorial. Well, this is just 2n times 2n minus 1 times times 2 times 1 again. So the difference is that this number will always be either not negative, an even or an odd number. Nevertheless, this is always guaranteed to be an even number. So how do we do this? Well, we can just say, okay, instead of k, let me just plug in 2k. And let's see if this works. So this will be a product of k equals 1 to n of 2k. So what do we get? Well, we get 2n minus 1, but hey, this does not work. Why doesn't it not work? Well, for n we do get 2n, okay, this is fine. But for n minus 1, we get 2 times n minus 1. But this is not 2n minus 1, this is 2n minus 2. Right? We distribute, and we get 2n minus 2. If we keep on going, we will actually get 2n minus 4, and so on up to 1. Sorry, not 1, up to 2. What's happening? Well, this is what's called the even factorial, or the double factorial. I'm not too sure right now, but this is not what we want. We will talk about this in our videos, but for now, this is not exactly what we want. So, how can we do it? This which would be the obvious, or not obvious, but the first guess, I think, at least it would be my first guess, does not work. So in order to make it work, we have to think a little bit. So we know that for k equals 1 and n, as we said, for 2k, this is, well, 2k times 2k minus 2 times 2k minus 4, and so on. But these are just the even terms. What about the odd terms? Well, hey, why don't we just do the same, but with the odd ones? And a way to put it is this, k minus 1. Why? Because we are missing here a 2n minus 1. Sorry, this should all be n, not k, okay? So n, n, and n. So what are we missing? Here we're missing a 2n minus 1. When we plug n here, we get 2n minus 1, okay. What's the next term? N becomes 2. 2k minus 2. Sorry, this becomes 2n minus 1. So 2 times n minus 1 is just 2n minus 3. Okay. But this was the term that was missing right here. And if we keep on going, we actually will get up to 1. So hey, I have the even terms, I have the odd terms, but I want them all together. So I can use the properties and multiply both products. And we will get that this is actually given by 2k times 2k minus 1. So this will be 2k times 2k minus 1. And this will be the expression for an even factorial. I hope that you can see, because I think the board is getting messy with the chalk, but well. So as you see, it's not too obvious, right? You see, well, why? Well, because these are the evens and these are the odd terms. But for example, for the n factorial, it's a really easy case and we don't even need it. What about the odd factorials? Well, let's say 2n plus 1, or you could also say 2n minus 1, but then in that case, you have to change the limits. But let me just call it 2n plus 1. How do we do it? Well, first of all, what is this? This is just 2n plus 1 times 2n times 2n minus 1 times dot. And wait a minute, this is just 2n plus 1 times all of this. This is just 2n plus 1 times 2n factorial, isn't it? So we can use the same expression, but we would actually get into some trouble because we need to add this term here. So it's not exactly too obvious how to do it. So let's try to do the first guess as we did before. So, well, one guess could be that we're going from 1 to n, and let's say, okay, why don't we just plug in 2n plus 1? Let's do it. 2k plus 1 instead, because we want to be multiplying. So, okay, we would get 2n plus 1. Okay, this first term is alright, and let me just erase this to not get confused. So, okay, this term is alright. What happens with n minus 2? Sorry, n minus 1. So we get 2n minus 1 plus 1, and this is 2n minus 2 plus 1, and this is 2n minus 1. Wait a minute, we run into trouble again. We are skipping the even terms. But hey, we know what the expression for the even terms is, don't we? We know that from before that 2k gives us the even terms, right? It gives us 2n times 2n minus 2 times dot times 2. So if we keep on going here, we will get, okay, 2n minus 1, 2n minus 3, and so on up to 1. So 2n plus 1, 2n, 2n minus 1, 2n minus 2, and we keep on going. So we have to multiply these two products. And let me just rewrite it here. So this odd factorial is equal to my pi multiplication symbol up to n of, sorry, and this should be 1. And let's talk about the indexes later on, and you see why it makes sense going from 1 to n, or from 0 to n minus 1, you see. So we have to multiply 2k plus 2k plus 1, because we are multiplying odd terms and even terms. So we have 2k plus 1 times 2k. So, okay. Another expression, another relation, okay. But hey, we added a 1 here, we added a 1 here, and then we just have to add a 1 over here. So maybe there's some kind of relations, kind of parameter, which we can make more general. Okay, so I think the video is getting too long, so I'm going to stop it right here. And in next videos, we'll talk about the more general form of these factorials in terms of the product, in the product notation, and where the gamma function comes in and how it is related to the product. Also, we'll see about some how to solve some recurrence relations using this notation and where they might come up. So, well, I hope you enjoyed the video and see you in the next one.